Okay, in this section 11-9, we're going to be talking about counting principles. And so the first thing that we're going to look at is the fundamental counting principle. And so what it says is if you've got two events, all right, and the first event can occur in m different ways, m sub 1 different ways, and after the first event has occurred, the second one can occur in m sub 2 different ways, then the number of ways that both of those events can occur is m sub 1 times m sub 2. So you take the numbers of ways that each one of those events can occur, and then the number of ways that they can occur together is just the product of each one of the individual occurrences. All right? And then, of course, if you had a third event, you would multiply by that third number, fourth, and so on and so forth. All right? Now, what we'll do is we'll go through and we'll look at all of these different principles that we're going to be looking at here today, and then we'll do some examples from each one. So the next two things I want to get into are the combinations and permutations. Now, many of you have probably studied these before in previous math courses, and of course we looked at combinations in the last section because it was a part of getting our coefficients to our binomial expansion, so we've just looked at this recently. But the main thing to remember is the main difference between combinations and permutations is in combinations, order does not matter. Okay. In combinations, order does not matter. In permutations, order matters. All right? So like in a combination, if I have 10 things and I'm choosing 3 of them, it doesn't matter which one I choose first and second. I just need to choose the 3. Okay? But in a permutation, like if I pick the same 3 objects, whichever one is first, and whichever one is second and whichever one is third matters. The order that I pick them in does matter. Because like if I take the same 3 objects and put them in a different order, that is a different permutation, but it's not a different combination. So keep that in mind. Order does not matter with combination. You just need the objects. Permutation, the order of the objects does matter. So if you switch the order, that's a different permutation. But if you switch the order, it's not a different combination. So thinking about that kind of makes you understand that the things that we use called combination locks are probably misnamed because you can't dial in the combination in any order you want. It has to be in the right order. So really they should be called permutation locks if you think about it, since the order that you put the numbers in or that you turn the numbers into the combination matters, right? All right. And then, of course, we'll get into this portion here. And I didn't really talk about the formulas here. So this one we've talked about before. So this is in elements taken r at a time, right? In elements taken r at a time. So it would be n factorial, the total number of objects or elements, over n minus r factorial times r factorial. And again, we worked with this formula in the last section, so you're probably still fairly familiar with that. For permutations now, all right, so P permutations, n chooses r, so it's the number of elements taken r at a time. Again, so for the permutation formula, remember the order matters in this one, it's still n factorial, but it's over n minus r factorial. And so the difference is you would leave this second multiplication off, the r factorial, right? And so that would give you the permutation. And so again, these two formulas will come into play. The main thing that we'll have to decide is when we come to a problem is whether it's a combination or a permutation. Now, there's another type of permutation, and that's called distinguishable permutation. So suppose a set of n objects has n sub 1 of one kind of object, n sub 2 of a second kind, and n sub 3 of a third kind, and so on. All right? Up to however many different types of objects you have. So the number of distinguishable permutations of the n objects would be given by this formula. So it's n factorial on top, and then n sub 1 factorial times n sub 2 factorial, all the way down to where you have multiply the factorial of every different number of types of distinguishable combinations that you have. And so what we mean by distinguishable permutations is a distinguishable object would be, like, for example, the classic example of this is if you have a word with repeating letters in it, I could switch those repeating letters around, but it's not distinguishable because it's the same letter. You see what I mean? So, like, for example, if I had the word, let's see, you think of a word with some repeating letters in it. Let's see. Let me think about this for a minute. What about elements, let's just say? All right. So elements, for example, has 3 E's in it. Okay. So if the question was asked, well, how many different ways can permutations can I take these letters in it? Well, if I switch the first E and the second E, that's technically a different permutation. All right. But it's indistinguishable because it looks exactly the same. It looks like the same output. You see what I mean? So that's what we mean when we get when we say distinguishable permutations. All right. And so you'll see what we mean when we get to an example for that one. All right. Okay. So here's the first type of problem that we come to. All right. So telephone numbers in the United States have 10 digits. The first 3 are the area code, and then the next 7 are the local phone number. How many different telephone numbers are possible within each area code? All right? And so one thing to remember is that a local telephone number cannot begin with a 0 or a 1. Okay? So we want to know how many different telephone numbers are possible within each area code. That's what we're trying to figure out. And so the first thing that we've got to decide here is, do I use a counting principle to come up with this, or a combination, or a permutation, or a distinguishable permutation? Because that's the 4 different types of things that we've looked at. Well, here it kind of tells you in the title. We're going to use the counting principle, right? Which means, okay, based on the events, we just multiply the occurrences of each one together. All right, so let's think about this for a minute. Okay, now remember, it's within the area code, so we don't have to worry about the first 3 digits. Okay, but the remaining 7, okay, we're going to have to figure out. Now, here's what we got to figure out. For the first digit, okay, how many different ways or how many different numbers can that first digit be? Remember, it can't be 0 or 1, but it can be 2, 3, 4, 5, 6, 7, 8, or 9, right? So if you take out these 2 digits, that means the first digit has 8 more choices left, right? So there are 8 different ways that that local phone number can begin. Now, how many ways does it have to choose for the second number in the local phone number? Well, all 10 digits are available for that one. Now remember, according to the counting principle, what do I need to be doing with these independent events, the number of ways they can occur? I got to multiply them together. So it's going to be 8 times 10. What about for the third number? I've got 10, so that's times 10. So that takes care of the first 3 numbers. But remember, I've got 4 more that can go 10 times 10 times 10 times 10. All right? So the number of different phone numbers that's possible within each area code would be the product of 8 times 10 times 10 times 10 times 10 times 10 times 10, and it's going to be 8 million. All right, so each area code has 8 million different possibilities of area codes within it. All right, so that's kind of the example of the counting principle. Remember, however many possibilities or choices you have for each element, you will take those and multiply them together, and then that would be how many that you would have total for the full set of events. Okay? All right, so let's look at the next problem here. It says a standard poker hand consists of 5 cards dealt from a deck of 52. How many different poker hands are possible? All right, and so it also tells us here, after the cards are dealt, the player may reorder them, so the order is not important. Okay, so that gives us a clue to what we should be using here to figure this out, plus the title of the question tells us it's combinations of n elements taken r at a time. So we know we're going to be using a combination here. All right? And so for my combination, I need to figure out how many things I have total to choose from and how many I'm taking at a time. Well, there are 52 cards, so this would be a combination of 52 chooses. How many are we going to be picking at a time? You're going to be picking 5. All right, so 52 chooses 5 is what I need to figure out here. Okay. Well, going back to my formula, it's going to be n factorial on top. So the top of the fraction is going to be 52 factorial over. All right, now the rest of it is going to be n minus r factorial. And so 52 minus 5 is going to make 47 factorial times. The rest of the formula here is times r. So r is 5. So that's times 5 factorial. All right? And so from here, we can just put factorial into the calculator. Desmos does have a factorial operator on it, so we can just go straight to our calculator instead of multiplying all these things back out. I do need a fraction, so it's going to be 52. To get to the factorial, you have to press A, B, C, and then, and then it's here. Can't see where I'm doing that, but after you press the ABC button, then it's down here. And then, of course, on the bottom, I need 47. Oh, I hit that in the wrong spot because I moved out of the way. Let me just start all over. All right, so I need 52. We'll go here. There's the factorial. Come to the bottom. Need my numbers again. 47 factorial times 5 factorial. And then, so there's our answer. It's 2,598,960. All right. And of course, don't forget that Desmos also has a combination calculator on it under stats right here. We could have just gone straight to here and put 52 chooses 5, and then we would get the answer that way as well. So 2 different ways to figure it out on the calculator from there. All right, so that's how many different poker hands are possible, right? All right, so the next thing that we're going to be looking at is this example. It says 8 horses are running in a race. In how many different ways can these horses come in first, second, and third? Okay, so how many different ways can these horses come in first, second, and third? All right, so once you see that the question is about an order of finishing, then that should alert you that order is important, and when order is important, then we know we're dealing with a permutation. All right, so here we need to have a total amount, which is 8. So this is a permutation of 8 chooses 3. So we need to see how many permutations are available when I choose 3 from 8 objects. All right, well, let's see. So on one like this now, we'll come back to our formula. And of course, it's n factorial on the top. So we'll have 8, because we've got 8 total horses, over. And on the bottom, it's just n minus r factorial. And so 8 minus 3 is going to be 5. 5 factorial there. And so we can finish this up now pretty quickly. Come back to our calculator here. Get rid of these. Go with a fraction. We need 8 factorial over 5 factorial. So 336 different ways is how many different ways that 8 horses can finish first, second, and third, with the order being important. Okay? Then, of course, you've got a permutation calculator that you can use as well. We go over to functions. Permutation is here. And then we can go 8 chooses 3. And then notice we get the same answer, 336. Okay, so this last question now is about distinguishable permutations that we were talking about last time, and how many distinguishable ways can these letters in the word banana be written. Okay, so now remember, the formula for distinguishable permutations is, all right, the number of objects, total number of objects, factorial, over, okay, each one of how many different kinds of objects you have, factorial times each other. So when we're looking at this, the first thing that we need to decide is how many different types of objects that we have. And like I say, the reason why this is important is because I've got like 3 A's here. So if I switch these 2 A's, technically that's a different permutation, but it's non-distinguishable because I can't tell which A is the first one and which A is the second one. So it looks the same, all right? So it's not distinguishable. So it really counts as, we want to see how many distinguishable permutations we have, not just total permutations, because it looks exactly the same whether the letters A's are switched or not. All right, so we need to see how many different types of objects we have. Well, how many A's do we have? We have 3. How many N's do we have? We have 2. And how many B's do we have? We have 1. All right, so in order to figure out how many distinguishable permutations there are in the ways you can switch around the letters in the word banana, okay, you've got 1, 2, 3, 4, 5, 6 letters total, right? And so that would be 6 factorial on the top, over, okay, how many A's do we have? 3, so that's 3 factorial, times, how many N's do we have? 2, 2 factorial, times, how many B's do we have? 1, so that's 1 factorial. And so if we figure that out, we'll see how many distinguishable permutations that there are. And so we can throw that into the calculator and figure that out pretty quickly. So we'll go back up here, and I'll turn this into a 6. Then down here I've got 3 factorial times 2 factorial. And I'm going to go ahead and stop there because 1 factorial is just 1. It's not going to change anything. So I know I have 60 different distinguishable permutations for the letters in the words banana, the way they can be rearranged. Okay? Now, just for comparison purposes, let's see how many total permutations there would be as far as, well, let's see, 6 objects choosing all of them. All right? So if I went here just to see like what the difference is, I could go permutations here, and I've got 1, 2, 3, 4, 5, 6. I could go 6, chooses 6. So there's 720 different ways that I could choose all 6 objects, but only 60 of them are different. So that just gives you a little bit of perspective there. All right? So that's it for this lesson. Your quiz will be waiting for you in Canvas.